Hello, I am Dr. Vinod Kallur, Army College of Engineering, Bangalore. In this video, I will introduce the idea of simulation-based learning. The example used here is a batch simulator, but the larger focus is not only on the batch reactor, but also on how simulators can help students move from simply calculating answers to observing behavior, interpreting trends, and developing engineering thinking. We will use the DOTS framework for the purpose, that is, do, observe, think, and then solve. With this background, let us start the video. In order to bring out the DOTS framework and how simulation-based learning can be brought into academics, let us use batch reactor as an example. We will also understand how conventional way of handling problems has limitations, thus creating a roadblock. We will cover how easily such situations can be handled by the simulator. Can simulators make students think? This is a larger question we are trying to answer in this video. Whether simulators encourage students to think or not will no doubt depends upon how the simulator is designed. The idea and the functionality of such simulators must be carefully chosen. In a traditional problem solving, students often move from formula to substitution and then to the final answer. That is useful, but it may not always create a need to observe, question, or interpret the behavior or inculcate critical thinking. In real engineering practice, an engineer does not begin with only a formula. The engineer observes the equipment, records readings, interprets the behavior, and then makes decisions. In addition, there will be a need for the engineer to think critically and constructively in order to address a situation or a problem. Simulation-based learning can bring this habit into academics. The student can change inputs, observe the result, ask why the behavior has changed, and then solve the problem. Further, we can challenge the students to do the exploratory study using the simulator and learn to inculcate engineering thinking. The routine burden of mathematical calculations can be reduced by the simulator so that the student's attention can shift to observation, interpretation, thinking, and decision making. So the purpose of the simulator is not only to get an answer to a problem, it is also to help the students interact with the simulator and develop thinking ability, which is of utmost importance in the age of AI. What is the DOTS framework? That is, do, observe, think, and solve. First, do. The student enters the data and runs one case. This is similar to starting a reactor with fixed amounts of reactants and known concentrations. The simulator also needs kinetic information such as rate constant and reaction orders. This amounts to the simulation of the task of putting the reactor into operation, that is the doing part. Next, observe. The simulator replicates the performance of the reactor and shows how it behaves. The simulator helps the student to see or observe this performance by way of displaying the relevant information in a suitable format. In this case, it is a graphical representation of concentration and conversion of A versus time. Then comes the most important step, think. Why do both curves increasingly flatten? What will happen if one reactant is halved and the other doubled? What if A is not a limiting reactant? Remember, all the equations student and textbooks derive will have A as the limiting reactant. The other case is not treated at all. Of course, such thoughtful questions may not occur to the students. Such thoughts or questions should be triggered by the teachers. All such questions push the student beyond formula substitution. Finally, solve. The student uses the simulator output to answer the problem and interpret the result. This may also involve answering some previously mentioned probing questions by running the simulator for various cases and observing the results. Thus, DOTS framework does not mean do, think, observe, solve in that order. Now let us take one batch reactor study case and see how it is conventionally addressed, solved, or analyzed. This is the statement of the problem. The reaction is A plus B giving products and it is non-elementary. Reaction orders are 1.5 and 1. Equal volumes of pure A and pure B streams are charged into the reactor. The initial concentrations of the individual streams are 1.5 and 1.7 mole per liter. The question asked in the problem is, what is the conversion after 2 minutes and 5 minutes? In the conventional method, we will use batch reactor performance equation. We will convert the rate equation in terms of conversion of A, which is a limiting reactant in this case. Since the composition changes with time, the equation is written in the integral form. Once the rate equation is written in terms of conversion, the integral has to be evaluated to find the conversion at the required time. This is how concentration of A and B in the rate equation are written in terms of conversion using reaction stoichiometry and initial reactant ratio M. The rate equation is first expressed in terms of conversion and then substituted into the batch reactor performance equation. For the case in hand, this gives one equation with one unknown, namely the conversion XA. The left hand side of the equation is known and its value is 0.8119. Therefore, the task is to find the value of XA that makes the integral value equal to 0.2119. However, the integral does not give a simple directly usable expression for conversion. So XA cannot be obtained by simple rearrangement or direct substitution. We have to assume a value of conversion, evaluate the integral, compare it with 0.8119 and repeat the calculation until values match. This creates a cognitive load of math. Instead of focusing on the core domain, the student's attention gets occupied by the numerical burden of solving the integral. This is the roadblock in the conventional approach. We will soon see how cognitive load of math is delegated to the simulator. Let us look at the simulator interface. The screen is divided into three main parts. On the left, we have feed information. Here, we enter the initial concentrations of A and B and the amount of the reactants charged to the reactor. Below that, we enter the stoichiometric coefficients. Reaction stoichiometry is an essential input. In the middle, we have kinetic information. Here we enter the reaction orders with respect to A and B and the rate constant K. Note that orders can be fractions as well. On the right, we have observation window. After running the simulator, we will observe how the concentration and the conversion of A change with time. There is a provision to set the simulation time. At the click of run button, simulation runs and the output will be displayed as curves of concentration and conversion versus time. Save button will save the output data, in this case a table of concentration and conversion versus time along with all the input values. Reset button will bring the simulator back to default setting with all values set to 0 and will be ready for a new case. So the GUI follows simple logical sequence. Input of parameters and setting up of the simulation followed by running the simulation, observing and then saving the output. Let us solve this problem using the simulator. The initial concentration of A is entered as 1.5 mole per liter and the initial concentration of B is entered as 1.7. Since equal volumes of pure A and pure B are charged into the reactor, we enter the volume of A as 1 and the volume of B also as 1. We then enter the stoichiometric coefficients of A and B as 1 each. Next comes the input of kinetic information. The orders are 1.5 and 1 respectively for the species A and B. The rate constant is 0.25. Note that all input values are compatible with mole unit for amount, minute for time and liter for volume. The simulation time is set to 5 minutes. The simulator responds with graphical solution as shown here. With the save button clicked, the simulator responds with a dialog box asking for the folder and file name for saving. The saving will be in an Excel workbook with the name specified by the user as run1. You can also see all the input values for the run have been saved in the first row. Concentration and conversion of A are both saved as columns against time. Conversion at 5 minutes is close to 0.45. The other task is to find conversion at 2 minutes. In the saved table, T is equal to 2 lies between 1.658 minute and 2.211 minute. The corresponding conversions are 0.225 and 0.2763. So the conversion at 2 minutes lies in between. We can find it by interpolation as an approximation. Alternatively, we can run the simulator again with all input values unchanged and only change in the simulation time to 2 minutes. This is a useful way of handling simulator output. It is not just reading the numbers mechanically, but decide how to use the saved data creatively to address an issue. Now we repeat the simulation for second required time. All the input values are kept the same. We change only the simulation time from 5 minutes to 2 minutes and click run. The simulator now gives the concentration and conversion profiles up to 2 minutes. After the 2-minute run is completed, we again click save. The simulator saves this in the same Excel workbook as a separate sheet run 2, while the previous 5-minute result is retained as run 1. Again, all input values are saved at the top and output table is saved below. At 2 minutes, the conversion of A is approximately 0.258. So by running the same case for two different simulation times, we can obtain the required conversions at 2 minutes and 5 minutes and compare the results. Let us summarize what we have done. We did not use the simulator only to get one numerical answer. We used it to observe how the batch reactor behaves with time. We saw how concentration and conversion changes and the saved output that can be used in many different ways. This is a real value of simulation-based learning. The simulator reduces the routine calculation burden and gives the student a space to observe, question, interpret, and solve. So the larger message is this: a simulator is not just a calculator. It's a learning environment that can help students develop engineering thinking. That is the core of DOTS framework. In the next video, we will see how the same simulator, without any change in its functionality, can be used for exploratory study and deeper engineering thinking and analysis. Before closing, some food for thought. This is a part of the graphical user interface of the reactor where we have to do some input. Now, why there is no input of reactor volume? There is volume of A and volume of B. There is no reactor volume. And why there is no provision to enter the stoichiometric coefficients C and D, though the stoichiometry has C and D. Can we use this simulator to study the case of A giving R reaction, that too first and zero orders? How about A plus B giving R with orders for both A and B 0? Thank you.